Welcome to the first lecture on high-performance scientific computing. Today we will explore what is high-performance scientific computing, what is the need for high-performance scientific computing, what is the contribution of high-performance scientific computing to science and the development of mankind in general. So the history of science goes back many millennia. Over the last millennia, science has advanced through various means, but primarily through theories. In this slide, you can see the cartoons of two very famous incidences in the history of science. On the left side, we have Archimedes, who is slipping into the bathtub and is yelling out, "Eureka!" The story goes is that the local king had asked Archimedes to find out whether the newly minted crown is made of pure gold or not. Now, it is very easy to find out the mass of a crown by using a simple balance scale. But how do you find out the volume of the irregular shaped crown? Because the only way to determine whether the crown is made out of pure gold or not is to verify the density of the object. And to verify the density of the object, you need both the mass and the volume of the object. So while Archimedes was wondering about this problem, he sat down into this bathtub and then he realized that there was some volume of the fluid, which is water, being removed or displaced. And then through this observation came the theory and the laws of buoyancy. And Archimedes was able to tell the king whether his crown was made of pure gold or not. On the right side, you have another interesting incident from history where you have this apple which supposedly fell on Sir Isaac Newton's head. Now, one would wonder, why does the apple fall down? Why does it not go up? Sir Isaac Newton wondered the same thing, and he pondered about it for a long time and came up with the laws of gravity. Now, here, science has advanced by looking at observations and then coming up with a theory to support these observations. The other way science advances is that one comes up with a hypothesis or one comes up with a theory, and then you conduct experiments or you try to construct these observations which will then prove this theory. On the left side, you have the setup of the Large Hadron Collider. The Large Hadron Collider is a large particle accelerator which is based in Switzerland and France at the CERN laboratory. And one of the primary goals of this very large experiment was to find out the existence of the Higgs boson, which was hypothesized a few decades ago. Similarly, on the right side, you have a water tunnel experiment. In this water tunnel experiment, you have an immersed torpedo where you're trying to figure out what the coefficient of drag or the drag laws are, or rather verify and validate the hypothesized drag laws are accurate. And this is very important in propulsion. Now, in the last century or so, there has been an important addition to this support of science. For millennia, the only way we could advance science was either to come up with theories after making certain observations or hypothesize something and then come up with experiments to verify those theories. But today, we have a third important leg which supports the stool of science. That is computational science. So where we can create a lot of these experiments in a virtual world where we can define the laws and make certain observations. So what does computations actually mean? So we look at very large calculations which are being done on these extremely large supercomputers. This is a pictographic representation of one of the several supercomputers which are out there. But what these machines are essentially doing. See, the way the laws of physics are characterized is usually by the help of mathematics. You have a certain set of usually partial differential equations which describe certain phenomena. They could be natural phenomena or any other artificial phenomena that you want to study. Usually these partial differential equations do not have closed form analytical solutions, or the closed form analytical solutions are extremely hard to obtain. And hence we have to resort to what is called as numerical methods and numerical techniques to break down these large systems of partial differential equations into several sets of algebraic equations which then can be solved on these large computers. Because computers directly cannot solve partial differential equations. They have to be sort of broken down into smaller steps, into smaller algebraic steps, and then only they can be solved. Who are the people who are solving it? The people who are solving it are researchers and grad students like exhibited in this standard comic over here. Now, before we go into further details of high-performance scientific computing, it would be just to study a little bit of history about this. And more importantly, we would like to study the contributions of these four particular gentlemen. The contributions of these four gentlemen are immense in this field, but it's not sort of exhaustive. I mean, I picked these four people because I feel that they have one of the strongest contributions, but there are several other people as well who have contributed to this field. So let's begin by discussing a little bit of history of scientific computing. So the first person on the left of the screen is Alan Turing. Now, one would ask, what is the contribution of Alan Turing to high-performance scientific computing? So Alan Turing was the first one to propose what today we know as the Turing model, in which you basically have this abstract model of a computer where you have one bit of information which goes into a sort of a black box. It undergoes certain operations and then is put out with an output. Now, you could then change this entire series of operations into a series of inputs which go into this sort of a black box, has some sort of modification, and then comes out. So this Turing model is really, really important towards realizing what is called as general purpose computing, because you're essentially breaking down these mathematical operations of trying to solve these complex partial differential equations into simpler algebraic equations, but lots and lots of those, and then they have to sort of be solved in a sequential manner. We will get to the parallel computing bit in some time. Remember, what Alan Turing did was just a theoretical model. It had to be realized on a physical computer. And one of the first general purpose computers were designed by the next gentleman, Mr. John von Neumann, who was an engineer who realized a lot of these early computers using the generalized von Neumann architecture. The generalized von Neumann architecture gives us the framework of a general purpose computer, which allows us to take the Turing model and sort of implement it on the hardware. We will learn a lot more about the generalized von Neumann architecture in further lectures of this course and the implications of that as well. Now, one will wonder, when did both Mr. Turing and Mr. von Neumann did their work? A large part of the work was done during the Second World War, or around about that period of time in history. So about like 80 years ago. The next gentleman who is here in a sort of a much more dated photograph, his name is Alexei Krylov. Alexei Krylov was a decorated officer in the Imperial Russian Army towards the end of the 19th century. Now you would wonder, what is the contribution of a military officer in this area? Now you see, when you break down the complex partial differential equations into a set of algebraic equations, you have to solve what we know as simultaneous equations. So let us assume that we have a set of 3 simultaneous equations. We would look at what sort of methods are there to solve this set of equations. One of the most fundamental methods that we learn in a mathematics class is called as the Gauss elimination method. Now everybody remembers what the Gauss elimination method is. I will just approximate it at this point of time. Let's say that you have a matrix system, Ax is equal to B, and A is a 3 by 3 matrix. Okay, so X is a vector of 3 unknowns and B is a vector. What we need to do is we need to pre-multiply this system with the A inverse, and then we get the vector of unknowns, which is now A inverse B, because this becomes the identity matrix over here. Okay, now if A is 3 by 3, if you look at a 3 by 3 matrix, the technique that we do usually is we first convert, let's say that this matrix has certain inputs. Okay, so I will note this inputs as A, B, C, D, E, F, G, H, and I. Now this is the matrix A. So towards computing the inverse of A, I will first transform it into a sort of a upper triangular matrix. Let's call it E dash, F dash, and I dash. Right? So we do some sort of algebraic transformation through rows and columns. I won't go into the details of this because that's probably have learned in a linear algebra course. And then you go through the process of pivoting, you go through the process of back substitution, so on and so forth. What we are really interested in is how many mathematical operations we can do to make this transformation. And typically it is of the order of n cube to do something of a direct transformation. Now what does this mean and what implication does it have? So I have about 9 entries in this matrix. So the number of operations that, the number of unknowns that I have is about 3. So the order of operations that I typically have to do for a 3 by 3 matrix is about 3 cube, which is about 27 mathematical operations. Now this seems like a small number. But if you go back and to look at the kind of problems that we solve, so if you go back and look at the kind of problems that we solve, the typical number of unknowns is of the order of, minimally, the smallest problems that we look at is about 1 million. But this range can increase very quickly to 1 billion or even more than that, to 1 trillion. Okay? So the range of these problems that we solve, and we want to solve more and more with more and more unknowns. Now think about if you have a problem with 1 million unknowns, that means minimally the number of order operations, if I have to use a direct method, I'll have to do 10 raised to 18 calculations. These are algebraic operations. Now, the power of these supercomputers is measured using a unit called as flops, which stands for floating point operations per second. Now, one floating point operation is one algebraic operation, which could be addition, multiplication, subtraction, or a division. And typically these large machines are able to do operations of the order of 10 raised to 12 to 10 raised to 15 floating point operations per second. These are normal supercomputers. The world's fastest ones can do much more than that. But you can quickly see that how even a reasonably sized problem, which we said is of the order of 10 raised to 6, on a large enough machine could start taking a really long time if we used these so-called direct methods. So a problem which needs 10 raised to 18 steps would take on a machine which is capable of doing 10 raised to 12 calculations per second, roughly of the order of 1,000,000 seconds to solution. And this is an inordinately large time. So most reasonable problems will no longer be tractable to be solved on modern computers. How do we get around that? This is where the contributions of Alexei Krylov come in. So his contribution to the area of mathematics was in the area of iterative linear algebra solvers, where you take the problem from order n cube to about order n log n. And the way that is done is that you, instead of doing direct solves, you make a guess, and you would have heard about something called as the Krylov subspace solvers. So without these iterative methods, which were developed at the turn of the 19th century, you will not be able to use these modern computers to get some meaningful results. So you can imagine what sort of contributions Mr. Krylov had. The last contribution is from another person from Russia. He was part of the Soviet Imperial Navy. He was an admiral in that. And his contribution was towards a family of techniques to convert partial differential equations into a set of linear algebra equations. Remember that most of the phenomena that we are investigating in nature are modeled using partial differential equations. But these partial differential equations, which I need to remind you, do not have closed form analytical solutions because of the nature of their complexity. They need to be converted into a series of algebraic equations, which then are solved on this large set of computers. So Boris Gagarin, who was an admiral in the Soviet Navy, came up with several techniques, or what is called as the Gagarin family of techniques, to convert the set of PDEs into algebraic equations. And without the contributions of these four gentlemen, taking PDEs, which describe natural phenomena, and converting it into algebraic sets of equations, taking those algebraic sets of equations and tractably solving them in some sort of reasonable amount of time, and then finally realizing the mechanism and the computation machine to solve this, none of what we are able to do today would have been possible. So we must really thank all these four gentlemen for their contribution towards high-performance scientific computing. Now, let's look at the first sort of computing machine. So if you were to Google who invented the computer or who invented the first computer, typically the answer comes back as Charles Babbage. And this was a machine that was sort of designed by him. It's called the difference engine. Now, this was not a general purpose machine. The idea of the difference engine was that it would try to find out the coefficients of a polynomial which would sort of be fit to a set of data. Given a set of data, when polynomial curve fitting was being done, what the coefficients of the different terms in the polynomial would be, that's what the difference engine would actually compute. So it had a very, very specific purpose. It was designed for a specific purpose. The first real general purpose computer was ENIAC, or the first really large scale general purpose computer was ENIAC, which stands for Electronic Numerical Integrator and Accumulator. And you can see that this machine was an extremely large machine which is being housed in this large room. This machine was basically built using vacuum tubes and housed in a very large room. It also consumed a tremendous amount of power. One would wonder how many calculations was this machine capable of. So the computing power of this machine was of the order of 300 floating point operations per second. It was able to do 300 floating point operations per second, a significant number at that time. And the reason why this machine was used was to compute something called as artillery firing tables or ballistic firing tables. Now, what was the challenge? This is the era of the Second World War. And the idea here is that the soldier on the front needed to accurately point his cannon towards the target. Now, the only input the soldier could give is what is the vertical angle at which the cannon should be placed and what is the horizontal angle the cannon should be placed. Now, the accuracy of hitting the target depended on several factors. The first, obviously, is the distance at which the target is and the elevation at which the target is. The other factors that mattered were what were the wind conditions and what are the wind directions. The temperature and hence the humidity and thereon the density of air through which the cannonball or the shell had to travel was another factor. Right? So when you look at all these different parameters, the laws of physics which govern the accuracy with which the shell would hit the target was basically the laws of fluid mechanics, or more specifically, the full three-dimensional Navier-Stokes equation. The full three-dimensional Navier-Stokes equation, as is famously known, does not have a nice closed form analytical solution. So the only way to do that is to solve it on computers. Now, it's very obvious that the soldier on the front line is unable to do these kind of calculations, even with modern day computers at his disposal. So the only way to go about doing this was to sort of pre-compute all the possible scenarios and then hand the soldier a table. Because the soldier on the front line can definitely estimate the distance of the target, can estimate the elevation of the target, can estimate or measure directly the temperature and the wind direction speed. Using this as inputs, the soldier can then look up what is called as the firing table and then figure out what should be the correct vertical angle and horizontal angle at which the cannon should be set. All these calculations had to be pre-computed and supplied to the soldier in the form of a table. And that's what the purpose of this machine was. So you can see that this machine was built with a very specific application of building these firing tables, but in general, you could have large calculations done, large general purpose calculations done. Now, there has been a tremendous growth of computing power over the last few decades. As I said, this machine, which was built around the Second World War, was able to do about 300 floating point operations. In this plot, you can see that there is an exponential growth in the floating point operation capability of the machines through the decades. So in this graph, which we have sourced from a website called top500.org, it lists, or rather depicts, the fastest supercomputer in the world, the speed at which it is able to do the computations over the last few decades. It also shows you the 500th fastest computer. So this website basically lists the top 500 supercomputers in the world. And this list is released every 6 months. The red line shows you the fastest machine in the world. The yellow line shows you the 500th fastest machine in the world. And the blue line shows the cumulative sum of the power of the top 500 machines in the world. And you can see that this is growing dramatically. Today, the world's fastest machine is known as Frontier. It's located at the Oak Ridge National Labs in Tennessee, United States. And here's a photograph of me standing next to this large machine. I had the fortune of visiting this machine sometime in 2023. This machine is capable of doing a dramatic 1.7 exaflops. That is 1.7 into 10 raised to 18 floating point operations per second. The power that it consumes is of the order of 23 megawatts. This is electrical power, which is the size of a small town. And it has about 8.7 million CPU cores made up of this AMD EPYC 64-core machines. So you can imagine the scale of this machine and how big this is. And you can clearly see that even this machine, with its tremendous capacity of 1.7 exaflops, would not be able to do the simplest of problems if we were stuck with direct methods. And hence the importance of Alexei Krylov's work on introducing iterative methods to harness even this machine. And obviously, as the machine sizes grow, we need to wonder what sort of problems we are able to solve efficiently on such machines. Thank you.